Okay, this is what I wanted to also record. Okay. So this is interesting, this diagram that they're going to show us and everything they're saying in this. Now look at it this way, like, these look like what my photos look like from a long time ago. It's chasing a particle.
And hopefully in the next year or so, we'll discover how many and how massive they really are.
I'm smoking my bong too. Those look like inside of eyeballs. Oh my god, I saw a person! Did you see the person's eyes? I hadn't seen it before. Until then.
Interaction.
Wait.
Since the Higgs permeates are the quanta of the Higgs field, and they interact with all particles except the photon.
Did you see the person's eyes? I didn't see it before.
And hopefully in the next
it's over in this corner.
We will discover how many and how massive they really are.
Because it does. It comes out of our eyeballs. My eyeballs are activated. I'm onto them. And it fades away. I watch. Yeah, it's like a person's hat. It's like coming out of his eyeballs, going through the elements. All of our planets that are going around us are doing this to us people. Perhaps. Maybe that's what all the other planets are. But this is a cute little story here. Oh look, see, look, you're just banging into people too. They tie it into being a baby though. This is, but let's give her a whirl. Now we're on Earth, but we're each a cellular crazy thing too, you know?
Mechanics.
Do you two know how scientists identify the substances in distant stars? Do you know how we measure the composition of the sun, for example? Sure. One major tool is spectral analysis, isn't it? Yes, indeed.
I am familiar with the results of spectral analysis, but I am a bit unsure of how the spectra arise to begin with. Chaucer, is that part of our material for today?
Yes, it is, Diana. In fact, it is the starting point. Let's use Professor Peabody's Wayback Machine, since we don't have one of our own, and look at a little science history. Jeeves?
Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light, or spectra. For example,
how can I do
ordinary
this?
table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a
want
form.
that.
Meanwhile, the white light of the sun was also being examined closely.
So what if I
In
put certain...
1802, it was discovered that the solar spectrum itself had tiny gaps.
Kind of what I'm already doing now?
There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. Traveling forward from that era to a little over 100 years ago, scientists were examining the colors of light given off by solid heated objects.
Sorry about my coughing.
They discovered that these hot solids gave off continuous spectra, and that the overall color of the light revealed the temperature of the object. Now this was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects
Look, listen to the sound. It sounds like a plane.
almost perfectly, in fact. They were called black bodies because they absorb virtually
Right. Now think of all the sounds that are induced around us.
all the light that was shown upon their surfaces. These same objects also radiate almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can
Here's
see,
Delta
there
Blend.
isn't much light, and what light there is mostly lies out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object, and the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green to our cauldron of light on the right. As you can see, the combination so far looks yellow. This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap.
Okay, I gotta put this shit together now.
A heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside the kiln, electromagnetic radiation, light and heat, exist in a form of
listening
standing
to
waves.
quantum
Waves that,
mechanics
like the
while I
vibration of
screw
the
all
guitar
these
string, are attached at
computers
both
together.
ends. The ends of the standing waves, like the ends of the guitar string, do not move. They are anchored to the sides of the kiln.
And they create them
And many
through.
waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared.
That's why
We
it's been
cannot
so
detect
cold
it with
lately,
our naked
probably.
eye. But as the temperature rises, the kiln begins to glow red. And as the temperature continues to rise, the dominant color changes to orange,
Look at the
then
shape
yellow,
around it.
then bluish white.
Oh, shapes do certain
The
things too,
distribution of
probably.
energy and light shifts to shorter
Just like
wavelengths
sound will make
as the
certain
temperature
shapes.
rises. But there was a problem. The scientists expected the distribution of emitted light to continue to the increase at wavelengths toward the ultraviolet end of the distribution. It didn't.
It
Instead,
didn't.
there was less and less light given off as they were further and further into the ultraviolet. This was called the ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color.
Sound though. Ooh, and we have a
Standing
pink.
with the blue light, for
We've been having a
example,
pink and
can
blue
have energy equal to
sunset
0
light.
electron volts,
Okay, let's think of that. Pink and blue
or
sunsets.
3 electron volts, or 6 electron volts, or 9 electron volts, and so on. In general, energy equals any whole number, n, times Planck's constant, h, times the frequency of light,
So,
which for blue light is any
ooh,
number
V, and then you
times
think of
3
the
electron volts.
shape.
But notice, blue light standing waves cannot contain energy equal to 1 electron volt, or 2 electron volts, or 4 electron volts. Realizing that energy could have only discrete values was the beginning of quantum mechanics. The energy is said to be quantized, and n, from the equation above, is called a quantum number. Planck's conclusion that light energy is quantized was quickly used by Einstein to explain another puzzling phenomenon. It was known that shining a light upon a metal plate can release electrons from the plate. But the light has to have
Oh.
a certain wavelength
Okay,
before a
I
single
haven't thought of
electron
that.
is released.
But I'd have to wait till the sun hits
We
it
can
again.
shine brighter and brighter light on the plate forever. But if the color isn't right, the electrons stay home.
Huh.
Einstein concluded that the light striking the plate had to be coming in discrete bundles, and unless a single bundle had enough energy to free an electron from its captivity, it would remain trapped. And as
Ooh,
Planck has suggested,
not stuck in people's.
the
Okay.
wavelength and frequency of the light was a measure of the amount of energy each bundle carried. So while blue light packets might be able to free an electron, red light packets could not, no matter how many red packets hit the plate.
I just gotta figure out where am I gonna
But
put
wait
this
a minute.
computer?
That sounds awfully
Speed
like
up off the
light as a
ground.
particle and not a wave. And there are mountains of data showing light behaving like a wave. Diffraction, refraction, interference. Which is it? A particle or a wave? It is both. These light packets are extremely tiny. Let's call them photons, from photos, the Greek word for light. And when you try to explain the behavior of things this small, you must resort to really unusual ideas.
You were on the
The
ground.
idea is contained in quantum mechanics.
I don't think it's.
Now let's see how quantum mechanics helps us to understand atomic structure. Ah, Bohr and de Broglie are two of my heroes.
Boron who?
Cute, Diana. Cute. Jeeves?
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called a nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus.
Come across that.
Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen, when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed. In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, de Broglie suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength.
Okay, gotta figure
Second,
out.
these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
De Broglie's particle waves seem to answer many questions, but this was still not the final answer. No, the final answer is a brilliant piece of mathematics as well as physics. I agree. Jeeves, take it away.
A true giant of quantum revolution was Werner Heisenberg.
I need to
And from
connect.
the vagueness of positions of electrons in de Broglie's standing wave orbits,
How long
he
is
drew a
that
tremendous
fucking
insight,
whiteboard?
which he stated like this. The more precisely the position is determined, the less precisely the momentum is known, and vice versa. And while it may sound like a bunch of gobbledygook, it was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The question is often asked, what is it that is waving when a particle is described as a wave? And after a lot of hem-hawing around the issue,
Him
the
Holly.
answer is, existence is waving. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximum are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. While all important ideas necessary for quantum theory were established before him, it fell to the genius of Erwin Schrödinger to develop the equation that correctly describes the motion and behavior of all things this tiny. While Bohr and de Broglie managed to describe the hydrogen atom, Schrödinger's equation was able to describe hydrogen with the same detail. And then, it could go far beyond. It manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms and all the elements in the universe. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world.
Schrodinger's equation is really cool.
Yes, it is, Diana. I agree, but can we talk a little more about Heisenberg's uncertainty principle? Isn't there more to consider than the approach we use to describe it? Certainly, Kevin. Jeeves, let's have a closer look at that, please.
Werner Heisenberg did more than make a quantitative statement when he said that the particle's position and momentum could not be known simultaneously. He wrote an equation that quantified the relationship. Let's see how that information can lead to an easy understanding of the hydrogen atom described in exquisite detail by the Schrödinger equation. Without going into too much detail, let's look at a proton and an electron. Since the electron has a very tiny mass, it can occupy a very large region of space. Conversely, the proton has a very large mass, 2,000 times that of an electron, and therefore it occupies a very tiny region of space. The result is a quantum mechanical hydrogen atom, a tiny massive nucleus surrounded by a much larger cloud representing the electron. If we look at a simple graph relating the probability of finding the electron in a shell at a given distance from the nucleus, we find that as we travel outward from the nucleus, the probability increases at first as the shell expands. It reaches a maximum value and then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius where the probability reaches a maximum is precisely equal to the radius of the first allowed orbit of Niels Bohr's model of the hydrogen atom. And its energy is exactly equal to the energy of an electron in this orbit in the Bohr atom. So this is a very good picture of a hydrogen atom with an electron.